So if we were to show you a color-coded example of an ethane where each hydrogen is assigned a specific color, and if we were to take this, and this is my poor rendition of a propeller attached to a circular shaft, right, and you're looking at it face to face straight on in 3D space, right? If we were to compare these two objects, and we were to say that each color-coded hydrogen is going to correspond to one of the propeller blades on this propeller, all right, where obviously, you know, this corresponds to the blue hydrogen right here, and this green one will correspond to the green hydrogen. And if we were to imagine that there is free rotation around this single bond on this ethane molecule, what I mean to say is that there is rotation in this direction in a circular manner where both atoms can freely rotate. Both individual carbons, this carbon and this carbon, can rotate irrespective of each other. If we were to imagine that those kind of rotations taking place, and if we were to use our propeller as an example, what would happen to the blue propeller if it turned 1/3 of the way counterclockwise down this propeller or around the axis of this propeller? Well, we would get our blue propeller that would move down to the position of the green propeller, and we would get the green propeller moving to the position of the red propeller, and the red propeller moving to the position of the blue propeller. We would have a counterclockwise 1/3 revolution where each propeller moved 1/3 of the way along the axis, the circular shaft that it's attached to. This is the type of rotation that happens between carbon single bonds on all alkanes, and that's what the word conformation means. It just means it conforms in different ways depending on how these atoms rotate around each other. So if we were to use the actual ethane as an example, we would have the blue, and you know, keep in mind there's free rotation around this single bond. So we would have the blue hydrogen move to where the green hydrogen is, and the green hydrogen move to where the red hydrogen is, and the red one move all the way up to the original blue hydrogen's position. Depending on how these atoms and molecules rotate in such a way around single bonds is what determines things like the boiling point, the smell, the you know, a host of different qualities about this molecule can change depending on how this rotation takes place about the single bonds on straight chain alkanes. So this is an extremely important concept that we have to learn when dealing with alkanes and organic compounds. We have to understand that there is always, when dealing with single bonds, free rotation around those single bonds, and so each individual carbon can move in a way that is independent of the carbons that it's attached to due to its attachment to a single bond. So that opens up a whole nother dimension of analysis of the position and the shape of these molecules and what arrangement they take in 3D space, and that's what we call in organic chemistry conformational analysis. So now that we know that there's free rotation around the single bond on straight chain alkanes, and that these carbons can rotate in a way that the hydrogens around them will switch positions, what we should now ask ourselves are which conformations, or in other words, rotational arrangements in 3D space are more likely or less likely to happen. And what determines that is the amount of what we call in organic chemistry torsional strain around this single bond that the rotation causes on that single bond. So the ethane molecule you're looking at right here is in its I don't know if you would call it its rest state, or the rotational arrangement that causes the least amount of torsional strain on this single bond. Like if you were to take a rubber band and hold it on each end and twist only one end as much as possible and then let that rubber band go, the torsional strain will cause that rubber band to immediately go back to its original position, just an untwisted, unbent rubber band. And that's what I mean by torsional strain, is that some of these rotations put more pressure on the single bond bonding the two carbons than others. And there are basically two main conformations with an intermediary in between. And we call these conformations the anti-conformation and the eclipsed conformation. And I'm going to show you both conformations right now. And keep in mind, these are just rotations in 3D space. If we imagine grabbing this ethane molecule by the single bond right here in the middle and kind of twisting it so that our face is lined up directly with carbon number 1 here, we would be looking head on, straight on into this carbon, so that carbon number 2 wouldn't even be able to be seen because carbon number 1 would be directly blocking its view. Kind of like if I were to draw, and we call these Newman projections in organic chemistry, if I were to draw this signifying carbon number 1 and a circle behind it signifying carbon number 2, that's how we would be looking at it, straight on, straight forward. In each of these cases, here on the eclipse conformation and here on the anti-conformation, we are looking at carbon number 1, and here's carbon number 1's hydrogens, 1, 2, 3, and carbon number 2 is directly behind it, and here's carbon number 2's hydrogens, 1, 2, 3. So as you can tell, the anti-conformation basically has caused, and I'm going to go back to this ethane molecule, the carbons to arrange themselves in a way where, like in our tetrahedral molecule, our tetrahedromethane molecule, they have repelled each other as much as possible, and that's what causes the decreased or in this case non-existent amount of torsional strain on this single bond. The electrons on these hydrogens have arranged themselves in 3D space in a way that has delocalized, as we call in organic chemistry, the electrons surrounding the hydrogens. They are interacting. Carbon number 1's electrons on the hydrogens are interacting with carbon number 2's electrons on its hydrogens as little as possible. However, on the eclipse conformation, we see that carbon number 1 and carbon number 2 are directly behind each other, and their hydrogens are lined up perfectly, and that causes an immense amount of torsional strain on this single bond. The amount of strain that the eclipsed conformation causes on this single bond bonding the two carbons is the reason why the eclipsed conformation is so much more rare than the anti-conformation. And these are what conformations are all about, finding out which rotational arrangement in 3D space is more favorable on carbon compounds. This is one of the most important things in organic chemistry that you can know. And so now I'm gonna introduce you to Newman projections. Basically, I'm going to draw both of these eclipsed and anti-conformations in a way that we use in organic chemistry to kind of symbolize these molecules staring head-on in 3D space, so that we can draw them in their more favorable conformations. And like I was showing you here, when we draw Newman projections, and we're going to draw this ethane molecule as a Newman projection, we always draw a tiny little dot here to symbolize carbon number 1, and then we draw a circle behind that to symbolize carbon number 2. And then we draw the hydrogens of carbon number 1 in kind of like the Mercedes-Benz symbol fashion. We go one here, and one here, and all of these represent hydrogens. If we want to draw the anti-conformation, then we would have to draw this molecule assuming that this here, this big circle here, is carbon number 2, and we would draw its carbons like this. We draw them kind of coming out in the back here in the anti-conformation. And if we were to draw the eclipse conformation, we would do the same thing, but kind of with the hydrogens matching the hydrogens from carbon number 1. So we would have here, here, and here we would have hydrogens. So hydrogen, 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 and hydrogen, for a total of the 6 hydrogens we find on an ethane molecule. What does end up happening when we see the eclipse conformation, we will start to see the back hydrogens on carbon number 2 start to rotate in this direction until it has reached this anti-conformation 180 degrees later down the second carbon circumference. All right, and we have another kind of intermediary conformation that I'm going to draw like this, that we call the gauche conformation, and that just means that if we have the carbon number 2's hydrogens coming out like this on the back, we have kind of this conformation where it has only turned 60 degrees. In that manner. So this is the anti-conformation. This is the eclipsed. And this is the gauche, spelled G-A-U-C-H-E, I believe. So that's the introduction to Newman projections, and we're going to use this to predict the geometrical arrangements, the stereochemical arrangements is what we call it in organic chemistry, of all types of molecules. It's going to be one of the important concepts in organic chemistry, and so I'm going to give you a bunch of problems in another video, but right now I'm just kind of trying to lay the groundwork for people to understand what the concept of a Newman projection and conformations are and why carbon tends to take these conformations. So to recap, once again, there is free rotation around these single bonds, and that causes these hydrogens to repel each other in a way that their rotational arrangement is ideal.